we are going to consider the other architectures, the other three architectures, series. What did we do yesterday? Shunt, series shunt. So series, shunt series and shunt. Okay. The general rules, once you understand the general rules, then the analysis becomes very easy. As you will see, the general rules are the following for identifying and analyzing a feedback amplifier. The first step is identify the architecture, whether it is series, shunt, or shunt series. So first step is identify architecture. Okay. Second one is identify architecture, then you have to take an appropriate model of the basic amplifier. So appropriate model of the basic amplifier. Let me explain what I mean by this. Suppose it is a series configuration. Series means voltage, the feedback quantity, feedback parameter is a voltage, isn't that right? Series. So input is a series comparison, which means voltages are being compared. So the input of the basic amplifier should be a voltage. Output series connection means current is being sampled, so the output should be a current, and therefore for the basic amplifier in a series the basic amplifier should be voltage to current transducer. Is that okay? This is what I mean by appropriate model of the basic amplifier. 3. Depending on the architecture, you take an appropriate model of the feedback network. Appropriate model of the feedback network. For example, in the series shunt that we considered, why did we take the H parameter model? Because the H parameter model allows a series circuit at the input, H11, H12, V2, and a shunt circuit, a parallel circuit at the output. Okay. Similarly, we will see that in all other cases a different kind of parameter will be needed. Sometimes a small z, sometimes a small y, sometimes a small g as in gravity. Okay. These parameters, small g has not been taught to you, I believe. Small g is the inverse of H parameters. Okay. G parameters are the inverse of H parameters, but we need not know that. Once we get the feel of the whole thing, the parameter identification would be obvious. With a little bit of effort and exercise, you need not do the third step. You can go right from the third to the fourth step. Fourth step is, after you do this, absorb RS, RL, the source and the load, and feedback network impedances, FBN impedances, inside the basic amplifier. Inside basic amplifier. Okay. That is, absorb them inside the basic amplifier. That would make the A circuit of the feedback amplifier. That would make the A circuit. Then analyze the A circuit and find out the gain A. This gain could be dimensionless, could be of the dimension of impedance, could have the dimension of admittance, depending on what model you have chosen for the basic amplifier. Then number 6, determine beta. Determine beta depending on the kind of connection that you have made. And it is always good to remember that in the absorption of RS and RL, no, I am sorry, in the absorption of feedback network impedances, the impedance that is seen from the output port will depend on whether the input connection is series or shunt. If it is series, then you leave it open. If it is shunt, short it. Okay. Similarly, for what you absorb at the RS end. Okay. These are the general rules, and once you find the general rules, then once you identify A and beta, you know what is the feedback gain, you know what is the input impedance, you know what is the output impedance. In the matter of input and output impedances, one has to be a little careful in the calculation. Let me make that caution also at this stage. Suppose you have a basic amplifier and you have Vs and Rs, maybe the connection is series. Okay. Now, what I actually need is this impedance, the impedance that is seen by the source along with its internal resistance. Okay. When I absorb Rs in the basic amplifier, obviously the Rs is killed, Rs is inside, and in the feedback amplifier what you find out is Ri without feedback and then Rif, both shall involve Rs, and therefore to find out the actual input impedance faced by the source in the total feedback configuration, you shall have to decouple the Rif that has been found out from its Rs component. Sometimes it will be in series. If it is a Thevenin voltage source, for example, Thevenin source, then it has to be subtracted. If this is to be converted to a current source, then Gs has to be subtracted from Gif. This you must do with care, but looking at the circuit it should be obvious what is to be done. Okay. These are the general rules. Now let us quickly go through the other three configurations. Yes.
Could you please repeat the last point?
Oh, last point was that when you absorb Rs inside basic amplifier, you have transferred this here to identify the A circuit, and therefore the Rif that you shall find out will include Rs. On the other hand, what I want to find out in the actual amplifier is what is faced by the source along with its internal impedance, and therefore the feedback input impedance will be different from what you actually want, and one is to extract the desired quantity from what you have found out. You see, the A circuit and the beta circuit, they are hypothetically constructed circuit, right? And why do you construct it? Because we want to apply the formula A by 1 plus A beta, or Rif equal to Ri multiplied by or divided by 1 plus A beta. Okay? Rather than writing node equations and loop equations for a complicated circuit, we break it up into the A circuit and the beta circuit and then find out all other parameters. Okay? If we remember these general rules, then you will see that the analysis of the other three configurations will be very easy. We take first the series. Now, obviously, if it is series at the input, we are comparing voltages, and therefore I have a voltage source. The ideal situation would be I have a voltage source, then I have a basic amplifier in which the input impedance is Ri, this voltage is Vi, and since the comparison is series, this would be my Vf with this polarity. I am considering negative feedback. Okay. Now, the output, if it is series, current is being sampled, and therefore the appropriate model would be a current source, A Vi. This A now has the dimension of conductance. Okay. And you might have its output impedance R0. This is the model of the basic amplifier, and then you have a series sampling. So, ideally this should be a short circuit. This is my I0 and this is my I0. Then what you want for the feedback network is that it should be a short circuit. So, the current here is I0 and what do you want here? Ideally you want a voltage controlled, no, current controlled voltage source. So, what you want here is a voltage source of value beta times I0 with this polarity. This is the ideal situation. This is the basic amplifier and this is the feedback network. How does it differ from the practical situation? In the practical situation, this is no longer a voltage, a current controlled voltage source, it is a passive network, and the source has an impedance Rs, the load has an impedance RL. Okay. Let me draw the practical network, practical series, then we shall be able to simplify. Practical series. We have Vs Rs this is the basic amplifier, then we have a load resistance RL, this current is I0 and there is a series comparison, and therefore I have a feedback network like this. This current is I0. So, in order to analyze this, let us follow these steps. Of course, one assumption that we have made, I think I should re-emphasize this, that the feedback network forward transmission is much less compared to the basic amplifier forward transmission, and the feedback network reverse transmission is much greater than the basic amplifier reverse transmission. All right. On the basis of this, we model the feedback network now. You see, one thing I can do very easily is to shift Rs to the basic amplifier and RL to the basic amplifier. If I do that, let me do this in blue. If I include RL here, then obviously this would be a short circuit. That is what I wanted. I wanted the output to be short circuited. Okay. If I shift Rs here, then this is a short circuit, and therefore in the basic amplifier Rs and RL come in series. Agreed? Now we have to include the impedances of the feedback network. Without going into any model, let me do this as a short as a bypass route, through a bypass route, without going into an appropriate model. We will argue what the model should be later on, but without going into this, you see what I should do. Let me draw the A circuit right from this one. The A circuit would be Rs, basic amplifier, and then RL. Now obviously what will happen is two resistances will come at the other end. Okay, two resistances, call this R22 and call this R11. Agreed? From the feedback network, that is, the feedback network impedances have to be absorbed inside the basic amplifier. Now what is R11? R11 obviously shall be the resistance measured at port 1 of the feedback network with this, with the port 2, no, open, port 2 open. Why? Because it is a series connection. All right. And R22 similarly shall be the impedance measured at port 2 with port 1 open. Okay. All right. So we have identified the A circuit, the B circuit, the beta circuit, the beta circuit. Is this point clear? No, sir. No. Okay. What I wanted to do is to include the impedances of the feedback network, the impedances of the feedback network in the basic amplifier. Now how do I do that? If there comes a series impedance here, I will put it here. How does the series impedance come? Obviously this is the impedance measured here with this port opened. Why? This is because the appropriate parameters here are the Z parameters, small z, the impedance parameters. Let me justify now the procedure. But before justification, can I complete this and come back here? Okay. Can I complete the beta circuit without caring what the appropriate parameters of the feedback network are? We can do it by following this rule, that if the connection is series, open it. If the connection is shunt, short it. And you have to include two impedances to the basic amplifier, and each of them is obtained by measuring at the appropriate port with the other port opened or shorted, depending on whether that connection is series or shunt. This is the general rule of thumb. You can say blind rule, but there is a justification. Similarly, for the beta circuit, what you want from the feedback network is, since the connection is series, you want since the input connection is series, what do you want from the feedback network? A voltage or a current? Voltage. So you want a Vf prime with this polarity, with these terminals opened or shorted? Opened, because it's a series connection. And you have here, what do you feed here? You sample current, and therefore you feed here a current source, I0 prime, and beta obviously would be equal to Vf prime divided by I0 prime. All right. Once you have done this, then you find out Ri, R0, RIF, R0F, and AF. Yes.
Why don't we directly use Vf? Why do we put a prime subscript over there?
Because I don't want to confuse this with the actual voltage. The actual voltage is different. Let me go back. The actual voltage is with the basic amplifier included, whereas what I find here is the open circuit voltage. So that may be different, that will be different. That is why I use a prime. Okay. Now I go back to why this rule works, because the feedback network here will have to be modeled as by its Z parameters. That is, let me go through this. Then in the other two, I will not explain what parameters I am using. Okay. Let me explain only in this one. The feedback network, why Z parameters? Because series, what I want is the equivalent circuit should be a series connection at port 1 and a series connection at port 2. And you know this is offered by the Z parameters and Z parameters alone. If I have V1, I1, V2, I2, then the Z parameters are V1, V2 equal to Z11, Z12, Z21, Z22 multiplied by I1, I2. And the equivalent circuit is, if you write this equation, V1 equal to I1 Z11 plus I2 Z12, you have Z11, then a voltage source with a value of Z12 I2. Then in the other circuit it would be Z22 and voltage source again Z21 I1, and this is plus minus. Then comes my basic assumption, that is the forward transmission through the feedback network is negligible compared to the forward transmission through the basic amplifier, and therefore this I make it equal to 0. Z21 takes care of the forward transmission. If I have a current I1, then there is a voltage here. Okay, and I include Z22.
So please can you repeat
why that is 0? That is not 0. What I am saying is, our basic assumption is the forward transmission to the feedback network is much less compared to the forward transmission to the basic amplifier, and therefore we ignored Z21. Agreed? Z21 takes care of the forward transmission. We ignored Z21 compared to the forward transmission through the basic amplifier. This is the first assumption that we make. Obviously, then we are left with Z22. What is Z22? is the impedance measured from port 2 with port 1 open. Okay, this is the justification, and there becomes a short circuit here, which is what my ideal series configuration is. There is a short circuit here. So Z22 goes back to the basic amplifier in the lower lead. Similarly Z11 goes to the basic amplifier in the lower lead. I absorb it there, and what I am left with, if Z11 is taken out there, what I am left out is a voltage source. This is what I wanted. Okay, to be able to measure Z12 or beta, Z12 is now equal to beta. To be able to measure it, what you have to do is apply a current source here and measure the voltage under open circuit conditions, and that gives you Z12. This is the total justification. In the other two, I will not make this justification. I will simply draw the A circuit and the beta circuit. But before that, let me take an example. Example of a series. It's a practical circuit. There is a chip called op-amp chip called 1533, and part of this circuit is a feedback amplifier in the series configuration, and it's a feedback triple. It's called a feedback triple. 3 transistors are used to form a feedback triple, and the circuit is this. I am drawing the simplified circuit. You have a source Vs which goes to a transistor Q1. Q1 has an RE1, and the feedback is applied to RE1, so that the comparison shall be series or shunt? Series. Okay, this we are already familiar with. Then this as an RC1, and let us say it is grounded. That is, it goes to the power supply. I am drawing only the AC equivalent circuit. The output goes to, this is all an part of an IC chip, so there is no capacitor anywhere. There is no capacitor, and these resistances also have to be very moderate values, not exceeding 10K. RC1 in the actual circuit, RE1 is 100 ohms and RC1 is 9K. Let me indicate these values later. Okay, let me draw the circuit first. Q2, this is grounded, and this has an RC2 which goes to ground. The third transistor Q3 has another resistance RE2 in its emitter, and the feedback is applied from here to here through a resistance RF. Q3 has a resistance RC3 which is grounded, and the output voltage, output is a voltage taken here, V0. Now let us see, let me first indicate the element values, typical element values. This is 9K, this is 5K, this is only 600 ohms, this is 100 ohms, this is also 100 ohms, and this is 640 ohms. This is the kind of values that you use in an IC chip. Now, why am I saying that this is a series? You see the current here, the current, output current, approximately the same current flows here, and therefore this is a current sampling. Okay, this also we are acquainted with. This is a very standard method, particularly in IC configurations. So it's a current sampling, and obviously there is a voltage comparison, and therefore this is a series. Now, without bothering about any of the steps and the rules, with a little experience, one can draw the equivalent A circuit and the B circuit. The A circuit, for example, if you look at it carefully, it would be the following. I am drawing the A circuit right by inspection. It would be the following. You have Q1 RE1. Now this RF is the feedback element. RF is the feedback network. All right. So RE1 shall be shunted by, if you want to kill this feedback, it's a series, so you have to open it, and therefore RE1 would be shunted by RF plus RE2. Is that clear? So all I have is RE1 parallel RF plus RE2 for the A circuit. Last point. Okay. What this impedance, the impedance of the feedback network,
that is R11.
R11, it would be the impedance looking from port 1 with port 2 open, which is simply RF plus RE2. In a similar manner, RE2 shall be supplemented by a parallel connection of RF and RF plus RE1. Okay. Once again it would be plus, right. The other part of the circuit is simply RC1, this goes to Q2, then RC2, and this goes to Q3. This now comes in as RE2 parallel RF plus RE1, and this goes to RC3, goes to ground, and this current is I0 prime. Why do you say prime? Because this is the A circuit. Okay. Now the A circuit, what you have to calculate is the gain, which would be, fortunately there is no source or load resistance here. If there was, then you would have included this here. Okay. Now the other thing is, how do I know that I have to calculate I0 prime by Vs? To confuse matters, output is shown here as V0. Why don't we calculate V0 by Vs? We would have made a mistake if I calculate V0 by Vs. Why? Because it is a series configuration, and the appropriate gain is the output current divided by the input voltage, right, which would have a dimension of conductance or admittance. So what you have to calculate is I0 prime divided by, I can use Vs, but to keep continuity, as I0 prime by Vs prime. Then the beta circuit. Okay, this is the A circuit. The gain calculation for the A circuit is a routine matter, and can be done by inspection. No analysis should be required. Okay. For example, for the first stage, let's calculate Vc1 by Vs prime. I'll simply indicate how to do it. If you have a problem, ask me. Now actual effective load is Rc1 parallel R pi 2. Okay, and there is a resistance here, and therefore the gain shall be simply minus beta 1 Rc1 parallel R pi 2 divided by R pi 1 plus beta 1, actually it should be beta 1 plus 1, but we ignored that, beta 1 Re1 parallel Rf plus Re2. Agreed? This is the gain of the first stage. Gain of the second stage, if I calculate Vc2 by Vc1, the effective load, the gain would be minus Gm2 multiplied by Rc2 parallel R pi 3 plus beta 3 plus 1 multiplied by this. Is that clear? You should be able to do this by inspection. That is the sure test of a student who has graduated through SCDS 204. Okay, you should be able to do it by inspection.
One question.
Yeah.
I have to place Vs by Vs prime in this circuit.
Oh, this is simply to keep conformity. I put it I0 prime. This is not the actual current, and therefore I put it here. I don't have to. But in general, if you had a current source, for example, at the input, then you had to convert it to a voltage source, and that voltage source you will call it Vs prime, not Vs. Okay. Now for the third stage, I0 prime by Vc2, I0 prime by Vc2, what would be this transfer function? Yes, yes, minus GM3 multiplied by, it is the output current which is GM3 V pi 3. V pi 3 would be calculated from R pi 3 divided by
R by 3 plus
plus
beta
beta 3 plus 1 multiplied by this. Is that clear? Okay. So the gains you should be able to calculate by inspection. For the beta circuit, let us look at the beta circuit. It is what you have to apply is, beta circuit is simply this RF. This is the 2-port circuit, isn't it? What you have to apply is current source or voltage source? Current source. Let us call it I0 prime, and I am sorry, that is not the case. The beta circuit is this: RE1, RF, and then RE2. This is the beta circuit. By itself RF will not work. If RE2 is not there, it will not work. Okay. So this is the beta circuit, and I have to apply a current I0 prime and keep this open, and therefore beta here, this is VF prime plus minus, beta here would be RE2 again by inspection divided by RE2 plus RF plus RE1. This gives the current flowing through RF. This has to be multiplied by, yes, RE1, that is right. What I have done is I have found out the current through this branch by this proportioning, and the current multiplied by RE1, that is VF prime. So this is my beta, and once you know A and beta, you can calculate everything. Okay, now with those numerical values, no, let me check this temptation. Let us go to the shunt configuration. Shunt. In shunt configuration, what should be your source? What should be your basic amplifier? Shunt. Basic amplifier should have an input of current, and the output? Output is also a current. No, it is a shunt, voltage. So it should be a current to voltage amplifier, and therefore we choose the input source as a current source. And I am drawing a practical shunt. Okay, I am not drawing the theoretical one and then going over. I am drawing a practical shunt RS. Since it is shunt, I have the basic amplifier, and the output should be a voltage, and therefore I have the load resistance RL. This is the practical circuit. Then shunt means that I shall have the feedback network would be like this. Okay, this is the circuit of a shunt configuration. The first thing I do is what? I don't care. Now I will not model, I will not do anything. First thing I do is I shift these RSS to here, RS and RL, both of them. Okay, so I shift them here. Let me draw the A circuit directly from here. I won't go through any other process. A circuit would be the basic amplifier, and then you have RS here and RL here. The first thing is I absorb them and then I have to absorb the impedances of the feedback network. So the feedback network shall give two impedances R11 and R22. These will come in series or in shunt? Shunt, because it's a shunt configuration. So I shall have an additional R11 and an R22, where R11 shall be measured like this. Feedback network with output shorted. This is R11, and R22 shall be measured with the port 1 shorted and impedance looking here. Fine. That's the first thing. In the A circuit I don't need anything else. That's all the A circuit is. So I drive it by a current source, and what do I do with the output? I leave it open. So this is V0 prime, this is IS prime. And the A now is V0 prime divided by IS prime. Alright? The Ri of the base of the A circuit is this impedance Ri, and R0 is this impedance R0. You see, Ri includes Rs, R0 includes RL. And if I can now find the beta circuit and RIF and ROF, you have to take account of the fact that RIF will include Rs and ROF will include RL. You have to get rid of them. All right. This is a caution one has to exercise. But let's look at the beta network. From the beta network, what do you want? Do you want a current or a voltage?
Voltage.
No. I want a current because it's a shunt comparison. So my output port 1 should be open or short. Sufficiently confused. Short. And what should I drive it with? A voltage source. Okay. So I drive it with V0 prime. I short this and find out the current IF prime. Beta is IF prime divided by V0 prime. Okay. One check. Is this point clear? No. Let me go back. See, what you are applying here is a voltage, the output voltage, okay, V0 prime. And what you are getting is a current. Now, how do I find out beta? For beta, this has to be shorted and the short circuit current is to be found. Shunt means short. All right? Okay. One check in all this analysis, which you must keep at the back of your mind, is that the dimensions of A and beta should be reciprocals of each other. Why? Because A beta is dimensionless. A beta adds to or subtracts from 1. 1 is dimensionless. Okay? And therefore, does this check here? You see, A here is in ohms and beta is in moles. They have to be reciprocals of each other. If they don't, then you must have made a mistake. The critical point is the identification of the feedback. Once you identify the feedback, and nothing else is needed. A similar, the final configuration. Can you guess what parameters we used in? We short circuited that. Pardon me? Inverse of Z. That is small y parameter, because it gives a shunt connection at both the input and output. Now the last configuration, and then we will take an example. Last is a shunt series. Shunt series, which means that my A circuit, can I now draw the A circuit directly without drawing the practical circuit? Okay. A circuit, what shall it have? Basic amplifier. Since it is shunt series, current, and therefore what we shall have is RS in parallel. RS in parallel, and it should be driven by current source. Let's say IS prime. if the original source was a voltage source Vs and Rs, then you have to convert them into the equivalent Norton source. Now in the output it is a series connection, therefore what I want is a current, and therefore the load should come in series, that is right, RL. Okay. In addition to this, I should have from the feedback network R22. We will see how R22 is to be measured, and from the feedback network here an R11. Then what should I do with these two terminals? Short, and this is my I0 prime, and therefore in a shunt series the appropriate A is a current transfer function I0 prime by Is prime. Let us take the feedback network and identify R11 and R22. For R11, what do I do to these terminals? Open. And for R22, short. Right? We have identified the A circuit. We no longer bother about two-port parameters and how the basic assumption of course is that the feedback network forward transmission is negligible compared to the forward transmission of the basic amplifier, and vice versa. Reverse transmission of the feedback network is much larger compared to the reverse transmission in the basic amplifier. As long as that is obeyed, this circuit is valid. Finally, the beta circuit. In the beta circuit, the feedback network, what should you drive it with? Obviously, current source I0 prime, and what do you want here? Current. It should be shorted, and this is If prime, and beta is equal to If prime divided by I0 prime. Okay. Given any configuration, however complicated it may look, your ingenuity will lie in identifying what kind of feedback it is. Once you do that, then you can proceed blindly. Let me illustrate with one example. I will not calculate the full example, I will simply illustrate. Fairly elaborate, and I would omit the biasing circuits if you permit. I have a Vs Rs. This is also a practical amplifier. This is shorted Q1. This is RC1. Then we have a Q2, which RC2, this is the biasing resistance, and then you have an RL. This, well, I won't show the current yet because we want to identify. This is the RL and the voltage across. This is naturally we want a voltage at the output. Okay, fine. And the Q2 emitter, well, that comes across, that goes to a resistance Re2, and feedback is applied like this from here to here. Okay, there is also a chip that is available. Feedback is available like this. Now tell me what kind of a circuit is this? Obviously, this is a shunt. This is a shunt connection, isn't that right? It comes in parallel, it draws away some current from the source. So it's a shunt connection. No quarrel about that. Now what about this? It's a series because it is the current which is being sampled. Now which current should you consider? Obviously RC2 will be inside the chip. It's part of biasing. This is the current I0. Now it is not I0. Obviously I0 is being sampled because this current will be proportional to I0. Isn't that right? And this current would be approximately the same as this current. So, whatever this current is proportional to I0, and any quantity proportional to the output is called a sampled quantity. It may not be the total output current, it may be a part of the output current. So, it is a shunt series configuration. Is that okay? It is a shunt series configuration. Now, let us see if we can draw the A circuit and the beta circuit. If it is a shunt series, now what is the appropriate transfer function here? Before you apply those formulas, you must determine what kind of transfer. What is the appropriate transfer function? Current to current or voltage to current? Current to current, because there is a shunt here, and therefore first thing you should do is to convert this into its Norton equivalent. And so I have Is prime Rs, then you have the Q1 ground, R sub C1. What will come here from the feedback network? No, RE2, no more parallel, you have to open this. Let us have another resistance here. Usually feedback is controlled by a resistance Rf. Okay. So, what will come in parallel is Rf plus Re2. So, there would be a third resistance here, Rf plus Re2. Then we go ahead, we apply this to Q2, and we have, can we combine this? You better not, because then you lose I0. Is the point clear? Okay. So, you keep RL and make this as I0. Then at the emitter, this is Re2 shall be paralleled by what? Simply Rf, because the input is to be port 1 of the feedback network has to be shorted. So, it is simply Rf. This is my A network, and A is identified as I0 prime divided by Is prime. Find out the A network, then find out the beta network. Let us look at the beta network. For the beta network, you have Re2 and Rf. This is the beta network, nothing else. What do you want to apply and what do you want to get? Apply voltage or current? Current, I0 prime, and open or short? Short, and you find out If prime. Obviously, is it negative or positive? What is beta?
Negative.
And how much is this? Re2 divided by Re2 plus Rf. Once you find this A and beta, everything else fits into place. On Thursday, we shall work out some examples of feedback amplifiers.
Rolling is the process of producing different components by plastic deformation of work material by passing it between rotating rolls. The process is called longitudinal rolling if the forming rolls are rotating in the opposite directions and flow of work material is along the length of the job and perpendicular to the central line of the rolls. By this process, we can produce products like bars of different cross sections, steel for constructional work, Flat products like plates and sheets of various thickness can also be produced by this process. Another version or type of rolling process is transverse rolling. Let us have a look at a transverse cold rolling machine. In this process, the forming rolls are rotating in the same direction and the flow of material is either radial or the flow of material is along the axis of the job, which is also parallel to the axis of the forming rolls. A large variety of products like pulleys of different sections, rollers for overhead cranes, cycle freewheel, BB cups, gear blanks, and gears can be easily produced by this process. This machine can roll circular discs of aluminium, mild steel, and alloy steel of varying thickness and diameters. The two forming rolls are mounted on the spindles running in the bearing housings of the two blocks, one on either side of the job, and these blocks are moving in the dovetail slides of the main bed. In this process there is less material wastage, higher production rate and long tool life. Hence, it is much cheaper a process than any other conventional process.